So our first speaker today is a regular speaker for us, so thanks to AlexGrove. He has over 20 years experience in the EDA industry, having worked for Synopsys, ARM, Simplicity, Aldec, OneSpin Solutions, and Mentor Graphics. I think that's a full set, isn't it? He has experience in the design and verification of ASICs and FPGA functional safety and knowledge of the EDA industry. During this time at Mentor, Alex has worked as a product specialist for high-level synthesis and virtual prototyping, is now working as European application engineer for functional verification and functional safety with Mentor Siemens Business. Okay, I'm going to hand over to Alex. Thank you.
Thanks, Mike. So I had decided how I'd start this presentation, but I thought I'd be late this morning. And the reason I thought I'd be late is I left Reading about just after 9 o'clock. And as I was leaving, the traffic stopped. And then eventually I came up to find the cause of the reason. And there'd been an accident. And a young mother with a 18-month old, I'd guess, maybe two, daughter had been involved in an accident. A lot of people helping. And as you came up to the vehicle, then you realised what amount of damage had been done. The back of the vehicle had been crushed in, and I would suggest that the lorry had done that. And it really, everyone was okay, which is good. And it just made me think about what we're going to be talking about today, functional safety and road vehicles. The goal is safety and to keep people safe. And we're going to talk about a very narrow component of that, which is IC. And one of the things I hopefully will illustrate as Mentor, a Siemens business, and a Mentor merging with Siemens is a good thing. It's certainly a good thing for me. And I think you'll see it's a good thing for you, our customers, because it allows us to really demonstrate some key things that we talked about when we had the merger. One thing is we've been able to make investments in technology. In actual fact, for functional verification, my sort of area, we've made 3 acquisitions since we merged with Siemens. And then one of those things is acquisitions is a company called Temper, which focus on 26262, and I've been working with some key semiconductors in that space. Another thing, it demonstrates some of the dividends that we're now seeing of the investments that Siemens made into the business and the IC business, and the particular area I represent today, functional verification, talking about some of the things we've done in verification management. In actual fact, Ravi also talked about these acceleration of programs with the Symphony announcement that we did recently. And then finally, it talks about the synergies. So there are the natural synergies between Siemens and Mentor. When we talk about automotive and 26262, there's a lot of synergies there. There's even work that we do with TAS International that actually do crash testing, so very relevant to what happened this morning. And we'll talk about lifecycle management and introduce a product called Polarium, which is a capability that Siemens PL have had for some time. So as I'm first, I guess I get to introduce the topic. We have talked about functional safety at DVClub many times, and 26262. In actual fact, I think we were here 2 years ago talking about some of the things that we had done. My colleague Mark Handover presented what we were doing with Questa Formal in this space. I think the key thing about functional safety is it's about reducing risk, and the way we reduce risk is by eliminating uncertainty. And that gives us confidence. In DO254 speak, that would be considered, use the term design assurance. The reason we do that is the cost of failure is far higher than, say, in a consumer product, a phone or a TV. There are 2 faults that the 26262 specification talks about. One is systematic and one is random. There is something else that's coming that's not in the standard. I'm not going to talk about today. Malicious faults. Systematic faults are generally what we talk about at DVClub, about verification. Does the product do what it's supposed to do? The key thing, which we'll talk about in the context of any functional safety application, is we need greater rigor, and we'll talk about that. Something that's new and is a challenge is random faults. Random faults, we have to accept that the lifetime of the product could be 10, 15, 20 years, and at some point there will be a fault, and that fault could be transient, so something like a single event upset, or it could be permanent due to some form of like silicon wear out. And what's important is when this, or if this happens, that the product fails safely. And interestingly, it's only the hardware where we, in the specification, where we consider random faults. The random faults are part of the hardware. So a way of assessing functional safety, and there are many similarities actually to what we do in verification when I look at this, is we need some metrics, and some key metrics would be a fit rate, so a failure in time, or sometimes you see this term probability metric for hardware failure. So these are metrics that are used to assess the chance of an error. In automotive, there are seal levels A through to D, where D is where D has the greatest amount of risk reduction and therefore would be the safest level. And to measure, or to assess and to measure, we use a thing called diagnostic coverage. And diagnostic coverage is a way of measuring the effectiveness. So if we want to have, say, a single fault, which is, as it says, a single fault in the design, for the highest level, then we would need something that's higher than 99% diagnostic coverage. Latent faults, so latent faults is kind of example, we have two faults and they interplay. And the best example I can think of for this would be if we have a fault in the safety mechanism and a fault in the logic that safety mechanism is protecting, then that would be deemed to be a latent fault. Now, the chance of that happening is less, certainly in a time window, given time window, so that would allow us to have a lower diagnostic coverage for latent faults. Our approach to this for the so there's mental safe, which is a sort of overreaching goal or approach for functional safety. And today we're talking about the IEC with a particular focus on 26262. So if you're developing a safe IEC, then the first thing you have is your typical IEC development process, something we often talk about, various aspects in DVClub. But we extend that for safety, then there will be a parallel process which we refer to as a safety development process. I think the first thing to note is because of the increased rigor that we need, because of the cost of failure, then what we will typically find is that we drive the verification or the development through requirements. As well as that, I'm not going to talk about today as we're short on time. There's also a requirement for tool qualification. We need to be using tools that are safe for our systematic, so we're not injecting any errors into the process. So we would typically develop our product in much the same way that you develop any product that it operates correctly, but with greater rigor. On the safety side, then there is a parallel process where it starts with planning, analysis, and defining things like safety goals. And this is very much like in verification, you do analysis, you come up with a verification plan to drive that process. Much the same is true for the safety development process, where you're looking to see how could my design fail. It's failure mode analysis, and then to see what the effects are. What are the consequences of those failures? And then you would then need to decide how I'm going to mitigate that, and through the use of safety mechanisms. And then finally, you would then need to prove it. You have to demonstrate that those safety mechanisms are going to achieve the goals that you set out and that you're going to get the diagnostic coverage that you need in order to achieve your safety goals. And the output of all of this actually will be documentation, which you then take for the purpose of achieving compliance. So we call this our approach, or the solution that we provide for all of these aspects, mental safe IC. And I think this slide probably sort of illustrates that best. There are 4 key components. There's the life cycle management, so we need to manage the process from planning all the way to compliance. We need to help manage the safety analysis and automate what is generally a manual process using things like spreadsheets, and with safety analysis to set the safety goals. Once we've done that, we then would go into design for safety. We now have a capability to automate this process of injecting, adding those safety mechanisms into the design, and then finally we need to prove it with some form of safety verification. So lifecycle management, we've been able to leverage Siemens PL's capability of a product called Polarium. So that allows us to provide a full lifecycle enterprise solution from planning all the way to compliance. We have safety analysis through the Ostemper acquisition. We acquired some technology called Safetyscope, which has a number of capabilities to aid the analysis for safety. After we've done the safety analysis, we can then use that to drive the automation of inserting those safety mechanisms, so safety synthesis into design. And then finally, we would then go into safety verification, where we need to prove those safety mechanisms are doing what we set out to achieve. And what's interesting, we've added to our formal Veloce and TestCent capabilities a fault simulator from Ostemper called Kaleidoscope. I'm not going to say too much about Polarium. We're going to focus on really the requirement management and traceability, what we've done for VM, and that's just in VM in general. But it's important that you manage all these processes, and these are described in the section on supported processes in the 2626 standard. Things like managing change, managing configuration, establishing good workflows and governance, and things like audit and review. This actually happened very early on after the merger, where we started integrating our next generation verification management with Polarium. There was a natural synergy. We were doing things and it made sense to use Polarium for capturing the requirements. So what we've done from the Polarium environment, we will allow you to describe and capture all your requirements, and importantly the derived requirements. As you come down to something that's more atomic, less ambiguous, you will then export that into a verification plan using UCDB like we do today. You can then do your verification, and what's important with UCDB, that could be on any of the engines, so formal for static, Questa for simulation, or Veloce if you're using hardware assisted. You then export the results out of that platform back into Polarium, again using UCDB. And with that integration, that will allow you from Polarium to demonstrate that requirement has been satisfied, how that requirement has been satisfied, how that requirement was tested, and then most importantly, what the status of that test was. Safety analysis, what we would do is take in the design, which we might describe as unsafe. That would typically start as RTL, but most likely at the end be at the net list level for various reasons about what's the requirements of 2662 and a mission profile. The mission profile is used to compute fit rates, and I'm not going to go into details today. I have a slide just for your reference to talk a little bit about what that does. But using that mission profile, and I suppose something to think about, if the chip is inside the passenger compartment, it will be very different than if the chip is on top of the engine. So when you're doing those fit calculations, there will be differences about the environment. It will then guide you, and that's what's important. It's a guide. It is best case. I mean, this is early analysis in the beginning of the process, so it's best case, but it'll guide you where to insert your safety mechanism, so identify holes in what's called the coverage and contribution report, guide you where you should inserting your safety mechanisms and what type of safety mechanism to give you the numbers that you require for your safety goals. The fit example, I'm not going to detail today, but what's important is that we base this on IEC 62238, which is a standard for electrical and electronic. So design for safety, now we've done our analysis, we then have essentially a macro list which will tell you where you want to insert your safety mechanism and what type. Your unsafe design we call the RTL, and that will generate a safe design, so new RTL with the safety mechanisms automatically inserted. It provides some verification capabilities to verify the safety mechanisms that they are working, and also importantly provides scripts for a logical equivalence test to prove that you have not changed the sort of mission mode of the design. There are different types of safety mechanism that you can insert, and it depends whether you want the design to fail safe, so that be fail safe, or whether you want it to be error tolerant. So depending on what your goals are, and for example in automotive you often see things to be fail safe, so it's about identifying a failure and reporting that, whereas things like airborne electronics, you tend to have things that are fault tolerant, so they maintain operation on the presence of an error using things like TMR, some fault redundancy scheme. So the tools that we have, not going into too much detail, there's an ELIA and radioscope. I guess the point of this, without going all the things that you could do, and there are many different safety mechanisms that you can employ, and they are driven by your goals. I mean, replicating and implementing things like process and lockstep is very expensive. It uses a lot of silicon. So there are different safety mechanisms that you can put in place, and they will be driven by your safety goals, what you need to achieve, and ultimately that will be driven by the ASIL level that you're targeting for your product. But we have a product called an ELIA and radioscope, and really the way to think about that, radioscope is operating at the RTL level, so things that you can do to the RTL, whereas an ELIA is working at the macro level, so it's working with modules. Something to mention, obviously we have TestSense BIST and BIST type testing, and this would be a good example of where those sort of diagnostic type tests, built-in self-tests, work in conjunction with your safety mechanisms. And a good example would be that latent fault, where we might apply BIST to the safety mechanism for, say, a TMR scheme, and couple that with your safety mechanism, and that will be used so to allow you to mitigate for latent faults. So moving on to safety verification, so now we need to prove it, but before we actually go into that process, there is a fair amount of optimization that we can do on the fault list. And the fault list, and that can be for these chips, and you have the likes of NVIDIA now looking at targeting automotive with very large chips, can be very significant. So there'll be some optimization that we need to do to the fault list to optimize the process. And we do that in two places. One is Safety Scope, so that does some initial sort of fault list pruning. And as Mark Handover presented at this event a couple of years ago with the formal technologies, we can use formal to optimize the fault list to identify things that will be deemed to be a safe fault, for example. As well as that, then we have a number of engines. We also have formal for actually doing fault injection, which we've talked about at previous TVS events. Kaleidoscope is new, so that's a dynamic simulator doing fault injection that we've acquired from Ostemper. We also have the Veloce Fault app, Jagged's here from the Veloce team, that we've had European customers using. And also we add, with the acquisition with Kaleidoscope, something called HSE, and depending on time we may get the opportunity to talk about that, where we actually embed logic into the design for the purpose of doing fault injection. For fault simulation, we were taking our safe design, so our design that has the safety mechanisms inserted. And what's key is we do have an approach where we can mix RTL and netlist. Now we need to use netlist for the standard because that's deemed to be the closest thing to the silicon, but that's only for the problem that we're testing, which is the fault injection. So we can use a hybrid approach for things that aren't affecting that test, so the more stimulus generation, for example, we can mix RTL and netlist. And that simply will be done for performance reasons. We'll gain a performance benefit if we can use a hybrid approach. Taking our RTL sims, essentially vectors into the fault simulator, safety alarms where we're expecting to see alarms being asserted, and obviously importantly our fault list. And the outcome of that will be alarm triggered, which is good. So that goes into diagnostic coverage. So that's a credit essentially for diagnostic coverage. The error being masked, that means that we didn't see a change in the design, so therefore that will be deemed to be a safe fault. The alarm was not triggered, so that's a bad thing, that's unsafe, and then this option of not resolved, where for whatever reason it hasn't fallen into those three buckets. And an example of that could be the stimulus, so our RTL sims didn't actually toggle the node, so therefore we won't see, we've not tested that fault, and that would be considered to be unresolved. Or we have to consider, an important thing that we talk about is these chips will be multi-domain, we expect them to be mixed signal. So maybe there's an analog block is preventing that fault from propagating or something along those lines. So Kaleidoscope HSE, very briefly, this is a technique for embedding the fault. So one reason why you might do that, if the example of the analog block, you might use HSE in conjunction with our real number modeling capability. And that would allow you to essentially inject faults into an analog block and to see the impact of those faults being detected in the digital. I'm good, I'm ahead of time, Mike. So I always think it's best to be ahead of time. So in conclusion, really what I wanted just to illustrate today is Mentor Siemens coming together is a good thing, and that's really allowed us to address the whole problem. And what we are focused on is providing a solution that will enable you to get to compliance. And the goal is to get to compliance in less time and less effort. So that concludes the presentation. If anyone has any questions in the audience or online?
Thanks, Alex. Yeah, there's one question online. And the question is, does Kaleidoscope require SDF or delay annotation for netlists? Good question, no answer. So, but we can get the answer for you. We'll get the answer for you afterwards. That's the DJ. Okay. Any questions from Bristol audience? Do you want to go to Cambridge? We go to Cambridge and Grenoble. Cambridge, Grenoble, any questions, please?
So, quick question from Cambridge. So you say that you've got Mentor Safe Tool qualification. Are you qualifying every single revision of the tools that you release, or is it just specific ones?
Is that Chris?
Yes, that is Chris.
Oh, hi, Chris.
Change your answer.
No. There was one slide, and I always like to finish on time, or certainly ahead of time on these events. So, yeah, I didn't talk about certification. We do certify, and it is on a release. So what we've done is that we do a lot of QA, and then we have those QA back process and supporting documentation certified by TUSAR. So I think we're maybe on our third iteration. So we've just done 10.7. All this information is available on SupportNet. So you can have a look. And so for a given version of Questa, for example, or a given tool, you can download all the certification and information about what we've done for in terms of qualification. And if you need more for your goals, then we would work with you to ensure that you can satisfy what you need to do, which is to prove that the tools that you're building your chip on meet the requirements for 262 and compliance.
Okay, so you're doing 10.7. Are you doing 10.7a, 10.7b, 10.7c, or is it just 10.7?
I would have to check what the details are regarding the minor releases. So we would deem those to be minor releases. I would have to check, and actually that information would most likely be on SupportNet. That's a good question. I can find out for you, Chris.
Brilliant, thank you.
Thanks, Chris. Now we know who you are. Okay, and thanks to Alex as well for finishing on time. It's always good when speakers finishes on time. He's an old hand, so he's very good. So a big round of applause to just say thank you to Alex.